Hi, I promised I'd make you a video for independence. I'll try to do that real quick and not be too long with it. If any dogs start barking, then I will start again. In 2.1 and 2.2, in 2.1 we had learned the general rule for addition. Oh, I thought this would, here we go. Yeah, okay, so I guess I have purple on here. Probability A union B is probability A plus probability B minus intersection. So then we want a definition for probability A and B. So we said we could just cross multiply right here and multiply probability A intersect A given B by probability of B. So down here we had a new definition. Probability, let me see, I should be able to write now. This is the probability of A given B times the probability of B. But nicely, if we had independence, then I don't have to worry about conditioning. If we have independence, then probability A given B is probability A, and I can just multiply, probability A times probability B. And so it's a really nice case. And I know we had done this example 4 in class. We had done example 5 in class. We talked about the bonus. I didn't really say 6. I might have said it, but really fast. What's the probability I flip a coin once and get heads and then flip it again and get heads? So what I'm asking for here is what's the probability I get head, head, given I got a head on the first toss. So that's the probability, sorry, what's the probability 2 heads and head. So that's the probability of heads times the probability of heads and heads given heads. Ugh. Given, oh, it's all gone. Undo that. Okay, nice. Probably heads and heads given heads. Let's make this a little bit bigger. All right, but the probability of the first one is heads is a half times the probability head, another head, double heads given heads. The probability the second's a head given the first is head is still a half, because knowing the first is a head doesn't change the probability of the second. So this will be 1/4. And what I'm trying to illustrate right now, probably double heads given the first is heads is still a half times a half. So H and H are independent events. So that probably wasn't the nicest example. Let's go to a few more. So let's see. Let's get a nicer color here. Let's go to yellow. So independence, there's really 3 ways to define it. Probability A given B is probability of A. In other words, B does not influence A, so I'd get A back. Probability of B given A is probability of B. A doesn't influence B, so B's probability stays the same. Or when I multiply, I don't have to condition, and I just have probability A times probability of B. If you don't have independence, you have dependence. And okay, so determine if A and B are independent events in the following. So let A be the event of driving on ice, and B be the event of an accident. And if I look at one way, I definitely know the probability B given A, that's the probability of an accident given you're driving on ice, is greater than the probability of just an accident. So since these are not the same, since probability B given A is bigger than probability B, I'd say they are dependent. Okay, I like this example. These guys, maybe you know them from Smallville. Clark and Lex are friends. A is the event that Clark attends Lex's funeral. B is the event that Lex attends Clark's funeral. So, let me see. So probability of A given B. So what's the probability, given that we know Lex attended Clark's funeral, what's the probability that Clark will attend Lex's funeral? And we know actually that's 0, because if one attended the other, then there's no way they're going to turn around and come back. And 0 is not equal to the probability of A occurring, right? Oh, let me put that back in there again. This is not equal to P of A. So B, knowing B has occurred, definitely changes the probability of A, and I would say again these two events are dependent. Okay, a few little tougher ones. There's no nice way to show independence in a picture like mutually exclusive. You might want to be like, oh, I can tell by picture, but you can't. So here's another one. These are harder to think about. I'm going to throw two dice. One is red and one is black. Okay, so two distinct dice are rolled. A is the event that the sum is odd, and B is the event that the red lands on a 2. So here I have die 1, or the black die 1 through 6, and the red die 1 through 6. And in this matrix here, I put everything, every sum of the two die. So 1 and 1 is 2, 1 and 2 is 3, 1 and 3 is 4. So here's the sum of their outcomes. Again, we can do this a couple different ways, but I'm going to go with, what's the probability? The sum is 2, so let's check this one. What's the probability the sum is 2 given the red die lands on a 2? So B is the red die lands on a 2. So let's see, let's just choose another color here. Let's do this. Red die lands on a 2. So I know then I'm sitting in here. Okay, so then right now, let's go, I don't know if I'm allowed to write again. It looks like not. The probability of this is equal to, well, on the bottom now, I know it's 6. Right, I'm sitting here, and now what's the probability? The sum of the outcomes is odd, so there's 1. Let's go back to a marker again. Right, this one's odd, this one's odd, and this one's odd, given it's in that row. So that's going to be 3 out of 6. 3 out of 6, which is 1/2. The question is, does that equal to the probability of A? The probability of A is the sum that the outcome is odd. And in this matrix here, the sum that the outcome is odd is 1/2. So probability A given B is 1/2, and probably A is 1/2. You can check the other which way around, so I know then I have independence. Okay, one more. Do this one a little bit different. Here's probability of A, so let's just write those down. Probability of A is equal to 0.3, and probability of B is equal to 0.4. So the probability of A and B, you can see here, that's the intersection right in here, and the intersection is 0.12, and now the question is that the same as probability of A times probability of B? I'm using the definition that the intersection should be the product of them separately, and in fact 0.4 times 0.3 is equal to 0.12. So yep, I do have independence. And like I said, if you can see that, I can't see that from a picture. You really can't tell independence. You have to try these definitions. And if one of them holds, all of them hold. So I mean, I try one of them, the one that just looks nice to me, and if I can show that's true, I know all 3 others are true. So I hope that helps. At least it will help you get a little bit further with the homework, but I'll go over it again tomorrow. And the main thing is probably A given B. That's the formal definition if I don't have independence, but if I do, I can just multiply. So a lot of the homework, you have this simple, nice product because I tell you you have independence. Okay, let me shut off this video, and I'll see you tomorrow.